Hey guys, welcome back. Today we're going to look at how to find the area of regular polygons. So if you remember, regular means all the sides are congruent and all the angles are congruent. These are very unique polygons, so they have unique formulas. We're going to start off with a regular triangle, which is more commonly known as the equilateral triangle. And we've talked a little bit about this already. If you remember, even earlier this chapter, we used the regular area formula for a triangle, which is 1/2 base times height. And we just applied it to our equilateral triangle. So we drew our height down, and we said our height's going to be perpendicular to the base. And it's unique in an equilateral triangle because all the angles are 60 degrees. And when we drop the altitude, the top angle is bisected. So we actually create this 30, 60, 90 right triangle within our equilateral triangle. And so we're going to focus on that for a second. So our base and our height are going to come from this triangle. Our base is the side length S. So I'm going to plug in S for my base. Our height is the altitude that we drop down, and now we're gonna find out how to express our height in terms of S using the 30, 60, 90. So if you remember, the altitude bisects the base. So if this whole base is S, when we bisect it, we cut it in half. So it's kind of like saying S divided by 2, right? Both of these are halves of S. So if the side opposite the 30 is S root 2, we have this pattern for the 30, 60, 90, that it's whatever the side is opposite the A, we're going to multiply it by root 3 to get our side that's opposite the 60. So if our A is S root 2, what we're going to do is take that length and just multiply it by root 3, following the pattern of the 30, 60, 90. So we get that our height is S root 3 over 2. Okay, so now we have our base and our height, and we can multiply through. I'm going to just write S as a fraction since all the rest of them are in fraction form, just so we can multiply. When we multiply fractions, we multiply across. So across the numerator, it's going to be 1 times S is S squared times root 3. My denominator, 2 times 1 times 2 is 4. And by doing that, we get this general formula for the area of an equilateral triangle. Now, deriving this formula in general terms with the side length S, we've actually come up with a formula that we can use now no matter what the side length is of a triangle. If you take a look down below, we can apply this formula, side squared root 3 over 4, to both of these triangles. In letter A, we know this is an equilateral triangle because all the side lengths are congruent. Whereas in the beginning of the chapter, we were going to have to go through all of this work to find the area. Now that we know this formula, side squared root 3 over 4 will help us find the area. All we have to do is plug in 11 for the side. So it's going to be 11 squared root 3 over 4. 11 squared is 121 root 3 over 4. 121 over 4 doesn't simplify, so we just put our units and we're done. We've found the area of the equilateral triangle way faster than if we had to do all that work that we've been doing. So this formula is a nice shortcut formula for how to find the area of an equilateral triangle. We can use it with letter B as well. We know this is an equilateral triangle because all the side lengths all the angle measures are 60. So we can use side squared root 3 over 4 to calculate the area. This time, our side length is 5, so it's going to be 5 squared root 3 over 4. 5 squared is 25, and 25 divided by 4 doesn't simplify, so we are done. 25 root 3 over 4 square centimeters. So as far as our formulas go, all the formulas that we've been memorizing this chapter, here's another formula we can use, but this one only works for equilateral triangles. Okay, we'll add that to our study guide later on this week. All right, so that's for equilateral triangles. Now, we don't address it formally, but we'll just put a little bubble here. What about equilateral quadrilaterals? What is the name of an equilateral quadrilateral? Well, it's a square where all the sides and all the angles are congruent. Now, squares we know have all the sides and all the angles are congruent, and the angles are 90. So when we're trying to calculate the area, it's just a simple base times height. The difference is the base and the height are the same. So you can still think of it as base times height, or if they're both s's, just side squared. Both of those would work for your square. Nothing too fancy, just wanted to touch base so you know we're hitting all of our shapes. We have equilateral triangle, equilateral quadrilateral, which is our square, and now we are moving on to all the rest of them. So how do we find the area of a regular polygon, of any regular polygon? So this strategy will work for triangles and quadrilaterals, but really we're going to use this for pentagons, hexagons, heptagons, and so on. Okay, now I want you guys to just pause this here, take a screenshot of this and insert this in your notes, or just copy this down in your notes, and then unpause it so that I can explain a little bit further. Okay, so there's some really unique parts of our diagram, parts of our polygon that we want to look at, and each of these terms is one of those important parts. So the big things that we want to look for is that every diagram that we're going to be looking for is going to have a radius that we're going to have to identify, the apothem that's important, and then the half of the side length. So half of the side is this blue part. I'm going to call this blue part, the half of the side length, x. Okay, so when it's divided, when the side length is divided into two parts, that will be x. If you see, I know there's a lot going on here, but those three parts create this right triangle within our regular polygon, and we're going to use all of our strategies for solving right triangles to get all the information we need in order to calculate the area. And the formula we're going to use for that is 1/2 apothem times perimeter, 1/2 AP. So again, make sure all of this is in your notes. You can take a screenshot of it, you can copy it down, whatever you need, but make sure you're reading through it and you have it all down so that it makes sense. One of the other things I want to just point out is in this right triangle, the top angle we're going to need to use is this angle here, which is half of the central angle. So the central angle is bisected, and so we need half of it. And again, we're going to use this formula here, 360 divided by n, and then divide that by 2. All right, now that we have that all down, let's go ahead and try our first example. Now, what I did with my notes is I just inserted a sticky note over this whole part that was typed up. So go ahead and do that. Those are really good guiding questions, but I feel like sometimes it gets a little bit overwhelming, so I prefer to do it this way. All right, so first thing we need to pay attention to is what type of shape are we finding the area of? Well, in this example, this side has 1, 2, 3, 4, 5, 6 sides. This is a hexagon. It has 6 sides. Just like we did with all the rest of our formulas, we want to start off with the formula. If we're finding the area of a regular hexagon, we have to use 1/2 apothem times perimeter. And I'm going to go ahead and put my parentheses around the apothem and the perimeter, as those are my unknown values. And so I look at my diagram and I ask myself, okay, what am I given, and is there any information, am I given the apothem or the perimeter? Well, luckily in this problem we are given the apothem. The apothem is the segment that starts at the center and goes perpendicular to the side length, bisecting that side, and it is 5√3. They gave that to us, so I'm just going to plug it right into my formula right off the bat. I didn't have to do any work. That was really nice. The next value that we need is the perimeter. Now remember, the perimeter is adding up all 6 sides, right? But we don't know what the side lengths are yet, so that's what we need to figure out. Well, like I said before, we're going to focus in on this right triangle here, and part of the right triangle is this side length x, which remember is half of our side length. So if we can solve for x, all we have to do is double it to get our side length. And then once we know our side, there's 6 of those, we can figure out our perimeter. So we have a little bit of work to do, but it's we'll take it step by step. So if we have this right triangle, we can use Pythagorean theorem to solve. Since we have 2 out of the 3 sides. We can also, and I want to practice it this way, find this top angle measure to give us some direction. So remember, this top angle is half of the central angle. So the central angle can be found by doing 360 divided by the number of sides, in this case 6. So our central angle is 60 degrees. That's the whole angle. If we were to draw another radius over here that was 10, the central angle, that whole thing would be 60 degrees. But we don't need the whole central angle. We just need the top half of the triangle. And so the top angle is half of that, or 60 divided by 2, which is 30. So this top angle here is 30 degrees, which is really nice for us, because if we know that this right triangle is a right triangle with this top angle being 30, then that means this is a 30, 60, 90 right triangle. And so we can follow our pattern. This is 2a, this is a root 3. Really easily we can say that a, the side opposite the 30, is 5. So we were able to solve the right triangle using some background knowledge of right triangles and get that this blue segment, this part of the triangle, is 5 units long. And if that's 5, this is 5, which makes the whole side 10 units long. And if one side of the regular hexagon is 10, then all 6 sides are 10. So 10, 10, 10, 10, and so on. The perimeter, there are 6 sides. Each of them are 10 units long, so our perimeter is 60. And that's what I'm going to plug in over here, my formula for P. So the apothem was given to us. The perimeter took a little bit of work, but we were able to figure it out. And so now we just have to calculate what this looks like. Notice we haven't used our calculator at all yet. Now we're just going to multiply through. 1/2 times 60 is 30. 30 times 5 is 150 root 3. There are no units in our problem, so I don't need units in my answer. And so using 1/2 apothem times perimeter, we were able to come up with the area of this regular hexagon. Okay, let's try another one. So number 2, same sort of thing. We first want to figure out what shape this is. And again, I'm just going to insert a blank white sticky over this just to kind of make my workspace a little bit less cluttered. And I'm going to write right over it. You guys are welcome to fill in things if you like those guiding questions. So this shape, I need to know how many sides there are. So I just simply count 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 sides, which makes this an octagon. I start off with my area formula, 1/2 apothem times perimeter. And I'm just going to leave some blank spaces with parentheses so that I know what I'm looking to find. So I need my apothem. Now, if I look at the diagram, the apothem was not even drawn in. So I'm going to draw my apothem in. Remember, it's perpendicular and it bisects my side. And I'll label it A because I don't know what that is yet. What they do give me, though, is that the whole side length is 8. And so if the side length is 8, the perimeter is something I can calculate right away. There are 8 sides. Each of those 8 sides are 8 units long, so the perimeter is 64, or 8 plus 8 plus 8 plus 8, and so on, 8 times. So our perimeter is 64, so I can come up with my perimeter pretty quickly. So the bulk of the work that I'm going to have to use here is solving for that apothem. Okay. Now, in order to solve for that apothem, I do need to draw in that right triangle. So I'm going to fill in the rest. I'm going to draw in my radius for my hypotenuse. And so now I've created the right triangle. I know that if the whole side length is 8, it's being bisected by the apothem. So I can go ahead and write down that this part of my right triangle is 4. And the last thing that I need is this top angle of that right triangle. Now remember, the top angle is half of the central angle. So the central angle is 360 divided by 8. 360 divided by 8 is 45. And then I'm just going to go ahead and divide that by 2, and I get that my top angle is 22.5 degrees. That's that top angle of my right triangle. Now I need that because I'm going to eventually have to use trig to solve for this right triangle. So again, here's my right triangle. I know that this side length is 4, and my apothem is what I'm solving for. And so if you need to, go ahead and feel free to redraw that right triangle separately so it's not super cluttered. I know this is 4, I'm solving for my apothem, and this top angle is 22.5 degrees. Now, if I'm trying to solve for my apothem, I'm looking to solve for this right triangle. Now, 22.5 is not one of my special angles. I don't have enough information to use Pythagorean theorem. My only option here is trig. So if I focus in on this angle, 4 is my opposite side, A is my adjacent side, and so I know that the trig that I need to use to solve for my apothem is tangent. So katoa, so tangent of 22.5 is equal to the opposite side 4 over the adjacent A. Again, we use SOHCAHTOA, opposite over adjacent, to solve. So I'm going to use my shortcut that we've discussed, that we can just switch those spots with the variable. A is going to be 4 divided by tangent of 22.5. That's the value for my apothem in my diagram. So I'm not going to type it into my calculator. What I'm going to do is write that exact ratio into my formula here. 4 divided by tangent of 22.5. I don't want to use my calculator. I don't want to round yet because I want my answer to be as exact as possible. So I only want to round one time. And I'm going to write it out here because if somebody's looking at my work, hopefully it's pretty obvious where I'm getting all of my numbers. So at this point, once I have all of my values plugged in, now I can just simply type this in. 1/2 times 4, press enter. Divide by 22.5, press enter. Times 64, press enter. You should get that the area is 309 units. In this case, the tenths does round to 0, and so it would be units squared. Go ahead and do that. Try to type that in your calculator and make sure that you are getting the same decimal approximation so that we can make sure you're not making any errors with that. Okay, hopefully that makes sense. We're going to continue with some examples in class, but I just wanted to start you guys off and make sure you had a good solid foundation coming in, so our discussions, you can ask all your questions and kind of know what you need more explanation on when we're in class together. All right, hope you guys have a great day. We'll see you later.